Complete. Complete means the individual can identify their preference. So if you tell them, so if you give them two bundles, A and B, they can say A is better than B, B is better than A, or they're the same. You say, well, let me think about it, I don't know, which often happens, how can you put it in math? Makes sense? Impossible. So, we assume the preference is complete. It doesn't mean in the real result is complete. We assume it is. Otherwise, we cannot put it in math. Right? 2. We assume the preference is rational. That's called transitive. It follows through. Say, if you give them 3 bundles, they say A better than B, B better than C, then A must be better than C for them as well. If that follow through doesn't happen, they just mix up. Computer does not mix up. Math does not mix up. That won't be workable. We assume the preference is transitive too. See, we don't claim the consumers are actually having those. We claim without them we cannot do much. But these are required to set up what we call later utility function. Make sense? Okay. This is required. That's required. Number 3, we make it for simplicity, just to make it easier to work with. We assume non-satiation. More is better than less. That's not really required. That is just done to make it easier. Non-satiation implies you work with goods, not bads. More is better than less. Right? If you remove that one, you can still characterize the individual mathematically, graph it, everything is fine. We just we eliminate it for the time being. Right? The first one required, this is just done for simplicity. Anyway, the indifference curve is defined as locus of all bundles yielding the same satisfaction. And typically, not always, typically it looks convex multiplier. Typically. Can never be, well, cannot be upward sloping. If you assume those 3, there will be violation if it looks like this. What's the violation? The indifference curve, locus of bundles yielding the same satisfaction, cannot look upward sloping. If it does, it violates something. Which one is violated? Yep. Non-satiation. Because if it's upward sloping means more of one requires more of the other one to keep you as happy. Right? But you claim both are good. It doesn't work. Makes sense? So that violates non-satiation means one of them is bad. Which is quite possible in the real world you have a lot of bad stuff. Say if this was risk and this was reward, that's fine, that's a correct. Yeah, I'm running into white up there. That's a correct indifference curve for risk and reward. Make sense? If someone gives you more risk, you need more reward to be as happy. That's fine. We just assume that's not the case because we did this assumption to simplify. If you remove it, it's fine. Then it's fine. So there's nothing wrong with a rising indifference curve. But once it becomes bad, we don't want to do it. You're going to see this one if you ever do finance, because that's a setup for portfolio theory. You have someone having money, they care about reward, they don't care about risk. That will become their indifference curve. They will optimize their allocation of funds. That's used there. There's nothing wrong with it, but the third assumption we made, we leave it. Make sense? Okay. That's gone now. Now, if you graph if you graph the levels of satisfaction, right? To the right, it should make you happier. If you graph the indifference math, levels of satisfaction, to the right, it should make you happier. Which one of those three give you that? That's 3 levels of satisfaction, 3 indifference curves. I say to the right, the satisfaction will go up. This is happier than this is happier than this. Which one of these 3 will be that? One of those 3 assumptions leads to happier to the right, less happy to the left. Which one? Yep.
Incident?
No. Non-satiation, to the right you get more of both. That should make you happier, right? So if you go from here to here, you get more of both. That should make you happier. So indifference scale to the right, that gives you more happier. More happiness, right? Make sense? The way I graphed the indifference scale did not cross. If you graph it crossing, that's gonna validate something. You cannot graph it this way. You shouldn't have an indifference map that looked like that is not what I wanted. You shouldn't graph it crossing. That will violate something. Which one? Transitive. That is true if you assume you work with goods. If you assume non-satiation, the crossing indifference map violates transitive. Let's see how. This is bundle A. Take 2 bundles, all these, right? I put a straight line because y is the same for them. Just C, D, or X. Which one is better, C or D? If you agree with non-satiation, i.e., if you assume X is good, you work with good, then C should be more than. Make sense? So we assume non-satiation. If you assume non-satiation, then you get a violation here because this is equal to this. They are on the same difference curve. This is equal to this. They are on the same difference curve. As a result, this should be equal to this. That's not transitivity, but you cannot say it. You assume non-satiation. The follow-through doesn't work. Make sense? So if you assume you're working with goods, no satiation, you're going to violate transitivity. Make sense? A crossing indifference map means the individuals need to up. They cannot rank alone. Right? So you never graph crossing indifference map. Right? Make sense? Well, if you don't assume non-satiation, that's a follow-through. What's the violation now? If you don't assume non-satiation, the follow-through works then. What's the violation you get there? You get non-satiation violation. When you assume one, you violate the other one. Right? No matter what you assume, the other one is violated. So you cannot cross indifference curve. That's a no-no in economics. Right? Cross an indifference map, that means the individual has no idea what is going on. Right? They cannot rank properly, they don't know what is good, what is bad. Okay? From here up, go on graph crossing indifference map. A typical indifference map looks like the one I have, which is convex, smooth to the origin. It looks like this one. Why? It should should be downward sloping if you're working with goods. More of one compensate for less of the other one. You throw a good, right? It should be downward sloping. Does not have it convex, but most often is convex because of one economics law, which is applicable almost always, but not always. Which one? What economic law gives you convex smooth to the origin in the first curve? There's something that makes it convex smooth to the origin. Not one of those assumptions, not required, but happen all the time. Happen for most individuals, most cases. The log, diminishing, marginal, satisfaction. The more of something you have, the less satisfaction you get from it. That make the indifference curve convex smooth to the origin. Think about it why. Here, this individual has not much x, a lot of y. If you give him one more x, he's willing to give up a lot of y's. Here, he has a lot of x. Give him the same number of x, he's willing to give up far less y. The more we have, the less you like it, the less you give up for it. Thus, convex smooth to the origin, which follows diminishing marginal satisfaction. It's typical, not required. It's typical. A typical indifference curve with convex smooth to the origin due to diminishing marginal satisfaction. Right? The slope of the indifference curve, that's the slope of it, ignoring the sign, is called marginal rate of substitution. That tells you how much y he gives up for initial x. If you look at MRS here, it's very high. It basically means you really like x, you give up a lot of y for it. Here drops to small number. You still like x, but not much. You're not going to give up much for it. Make sense? So if you get an MRS of 4, what does it mean? So the MRS was 4. At some point here it was 4. What does it mean? It means you like x 4 times more than y. If someone gives you 1x, you're willing to give up 4y for it. Because you really like that, right? If MRS becomes, say, 0.1, you don't like it much. You only give up 0.1 for it. Convex smooth to the origin gives you MRS from sort of infinite all the way to almost 0. Right? Infinite means really, really like x, give up a lot for it. Going to 0 means, well, I don't care much. Although you give up a bit for it, not much. You give up a bit for it because of non-satiation. You always like it. So the slope goes from infinite, almost, not exactly, all the way to 0 due to non-satiation. No matter how much of it you have, you still get something from it. Make sense? Anyway, there are different mathematical characterization of preference. The first set of functions give you convex smooth to the origin. They are called group 1, class 1. They are the easiest to work with. Group number 1 will give you that graph. Easiest to work with, right? And very typical, used often. There are 2 functions in it. Cobb-Douglas is first. That is Cobb-Douglas. Invented by Mr. Cobb, Mr. Douglas. When did he write the paper? 1921, long time ago. Ages. That function is everywhere because it has very nice characteristics. Use it everywhere. Use it in production, you see it in the solar model later, in macro, you see it everywhere. The MRS for it is, remember this shortcut helps you later, because otherwise you will see in a bit. If you want to calculate MRS, you have to take derivatives. That takes time. If you remember the shortcut, then you basically have the slope calculated without doing derivatives. Make sense? The MRS for Cobb Douglas is that one. Independent R of X, R of Y, y X. Make sense? There's no dependent A. That's it. If you think about it, if you move along the curve from X around 0 to X around infinite, how does this moves? If you find very little X, a lot of Y, how much is this one? This is close to 0. This is very high. What do you get? Infinite. This is this end of it. If you increase X to infinite, this goes down to 0. That's sort of give you convex confusion. One end goes to infinite, never becomes infinite. The other end goes to 0, never becomes 0. Make sense? This gives you smooth, convex, to the origin. The other one is called CES. That is more advanced function. I say more advanced, but if you ever go to more advanced economics, they use this often. In the basic economics, they use a couple of us. In fact, you can show this embedded in it is this one. This is a special case of that one. So CS is widely used in advance. Anyway, the NOS for CS is this one. Yx 1 minus alpha. So A is irrelevant, beta is irrelevant. Right? The only thing that's relevant is alpha, the power of x and y. Make sense? Remember, the function should be like this. If this is sort of different number, that's not the same function. It has to be, the power has to be the same. If you want to find MRS for this one, if you want to take that derivative, it's not easy. It takes time. This is something to memorize. Okay? Again here, x to 0, this is infinite. X to infinite, this is 0. That's a convex configuration. So they give this for the same type of indifference. Never cross convex configuration, which is typical. Right? That's class number 1. I'm going to start with this one numerically when I go. Class number 2 are sort of extreme cases. Some consumers may look at too good at perfect substitute, i.e., MRS for them must be constant. Say, I exchange 2 apples for 1 orange always. Well, that individual MRS does not change. It's always the same. Make sense? Say, X is apples. Apples. Y is orange. Some consumers willing to exchange 2 apples for 1 orange always. Doesn't matter how much apple you have. How much? It's always the same exchange rate. How would the utility function for him look like? That looked like a straight line conversion. Make sense? A straight line looks like this one. Straight line. Make sense? That's the function that we call the fixed substitute. The MRS for it is alpha. I'll explain what the state case in a minute. Based on the example I'll give you, where the substitution rate is 2 apples for 1 coffee, what's the alpha over beta? What's the MRS for this individual? knowing that the MRS is the slope of the indifference curve, ignoring the sign. Use this one to figure it out. That's the MRS, the trade-off. Base and number given. What's the trade-off? 2? 1 over 2? 1 over 2 or 2? It's one of these two, right? You give up 2x for 1, that's the absolute value, that's 1 over 2. That's the statement, right? You are willing to give up 2 apples for 1 orange. The trade-off is you give up 2 apples for 1 orange, that's the MLS, 1 over 2. Yeah. You give up, yeah. But we don't care about the sign. The trade-off is negative. You give up, you get. I put the absolute value in the sign. So if the MRS is 1 over 2, the MRS is alpha over beta, the utility function becomes this. Right? That must be the utility function. Right? If you want to graph it, the indifference curve should look like this. That is 2 apples, that is 1 orange, that is 1 indifference curve. Right? 2, 1. And you can go to 4, 2. That is another one. And you become happier at this one. Straight line. Technically this violates diminishing marginal satisfaction. The satisfaction rate is the same. The trade-off is always the same. Okay? As I said, diminishing marginal satisfaction is typical, not required. It's not the assumption we have there. There are extreme cases. Right? Typically, the more of something you have, the less satisfaction you get from it. But there are extreme cases like this one. We look at now as perfect substitute. Make sense? For him, diminishing marginal satisfaction does not hold. Right? The other extreme is perfect complement. Perfect complement is someone who consumes 2 goods at specific ratio. Right? Say X is sugar. Let's see, X is coffee. X is coffee. Y is sugar. Someone who always consumes 1 coffee, 2 sugars. You give him 1 coffee, he needs 2 sugars. If you give him 2 coffee, he needs 4 sugars. Never goes outside that combination. Anything outside will be thrown away. If you give him 2 coffees and 2 sugars, the second coffee is thrown away. If you give him 3 sugars, 1 coffee, the third sugar is thrown away. He only consumes at that ratio. How do you write the utility function for him? That's the complement. Make sense? How do you write the utility function for him? That's hard. That's a knife edge type of utility, right? Okay. Let's see how someone did it. Write this relation. Mathematically write the line the individual wants to be on. Find the slope of it. Right? Based on the numbers given, what's the slope of that line? If this is 1, I want to get 2. What should be this one? What's the slope of the line that this individual stays on? How much is it? 2. If this is 1, I want to get 2. It should be 2. So someone said, write the utility this way. mean means if you depart from these two being equal, one goes up, nothing is achieved. Say, if I give you, this is sort of not the easiest thing in the world. If I give you one coffee, you need 2 sugars. How much your satisfaction would be? What does the function give you? If I give you one X for coffee and 2 sugars, you get 2, 2. The minimum is 2. So you get 2 meters. Suppose I give you now 2 coffees and 2 sugars. What do you get now? You get 4 and 2, but the minimum is still 2. That extra sugar, sorry, that extra coffee didn't do anything. Make sense? So that mean will give you the nice edge characteristic. Right? The graph then looks like this. I give you one coffee, you need 2 sugars. Right? You get some satisfaction equal to 2. Then I give you more coffee. Did that do anything? It didn't. You stayed on the same in the first case. If I give you more sugars, it doesn't do anything either. So that utility function gives you what we call L-shaped indifference curve. Right? From 1 coffee and 2 sugar, you get a satisfaction equal to whatever you get from these edges. But more of one does not do anything. More of the other one does not do anything either. If you want to move to a different level of satisfaction, you can. I have to give you how much? 4 sugars if you have 2 coffees. Then you move to higher indifference curve. Make sense? 1 increase doesn't do anything. I have to move them up, both of them, to stay on this line. Make sense? Anything that departs from that line, nothing is achieved. Right? Yeah.
Does that mean all these classifications?
0 is always 0. If I give you 0, 1, you need 0 the other one. The other one can be a million, does not give you anything, right? If I give you more coffee, I can give you a ton of tea, it does not do anything. Ton of sugar, it does not do anything. Good luck. So this is sort of not very easy to figure out. This is called the ONTF function. This is the one who actually characterized it that way. It actually was initially in the production, then came to consumption. We're going to leave it out until later. So I'm going to leave it out. I'm not going to work with it today. But you can think about it. It's a knife edge function. Knife edge function is very hard to actually put it in math, right? Someone did it and it looks very nice. Mean eliminates getting satisfaction from any increase in x and y outside of that equation. You're basically claiming if these two are equal, you get a satisfaction. The not, the more does not give anything. You hit by the mean. If you choose one without the other one, you're not going to get anything. That gives you the edges. Yep.
What does it say on the left of the brackets?
Where? Mean. This one? Where is it? This? That is min. Minimum. It's a minimum of whatever you get for those two numbers. Make sense? Okay. You get used to your own handwriting sometimes. You know, when was it? Several years ago, I cleaned up my old stuff. I had my PhD notes. history of economic thought. It was 8 in the morning. I think I was writing in a sleep. It was like scribbling. But it was like 10 people in the class. You cannot sleep there, right? So you pretend to be alive. And just do this. Anyway, but okay. The perfect complement is not, it's actually very easy to work with. It's just mathematical characterization is different. But not very hard to work with at all. We'll do it later. Yeah?
Yeah, just a quick question. The utility you calculated for a 2x and 1y, you just multiplied the
Yeah.
two utilities, right?
If I give you 2x, 2 by 1W2, 2 sugars will make it 2, that's 1. Anything outside that relation, you're not fine. Basically, anything outside is a waste. It's really cool. That is anything more x, anything more y. Make sense? This mean give you this part of it. If he says you should depart, you get no satisfaction. Anyway, perfect complement is another two. Third one is the weirdest one because it's not obvious what you get from it until you solve it. The third one is what we call quasi-linear, pure linear, quasi-linear or semi-linear. Quasi-linear is a function that is linear in x, not y, or in y not x, one of them. So this is linear in x, that's linear x, not y. See, the power of x is 1, that's linear x, but the power of y is not 1, that's quasi-linear in x. Or say this one, that's not linear in x, but linear in y. That's sort of a weird function because mathematically the indifference curves look like class number 1, convex and smooth. But it goes to a wrong quadrant. You may end up with something like this. That looks convex with the origin, but goes to the fourth quadrant. It doesn't stay in the first one. That may give you weird results when you optimize. We're going to leave it to later. Make sense? We're going to come back to it. Work with it. Alright, so I'm going to work with class number 1 today. Perfect substitute. Perfect complement. Quasi-linear will be later. I think lecture number 2 has a quasi-linear in it. There is a question from it that's actually quasi-linear, but I'm going to give it to you. Okay. So let's see what we did. I explained this. I did this. 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 We left out this. The consumer will try to increase their satisfaction. If there is no constraint, where do they stop? They never stop. Because of no variation. By definition, they're going to consume infinite. Fortunately for all of us, there is constraint. People have limited income. That is our constraint. That's the bottom part. Make sense? That's our constraint. You cannot go beyond it. Okay. How do you graph the bottom line? I had a terrible flu since last week. I think I got it from you. I never had it before. That was the first class. It must be from you. But I had the worst. The worst. Right? It's just recovering a bit, but that cough wants to come and try to suppress it. That's just a terrible feeling, right? Anyway, how do you graph the budget line? The straight line, right? If you want to graph a straight line, the best way is to graph the two ends of it and connect them. What is the x end of it? What is this end of the budget line? Based on the overall setup. What do you put there? Yes. Makes sense? What's the other end? I, dy. If you connect them, what's the slope of that line? I know it's negative. Ignoring the sign. What's the slope of it? It will be relative price. Make sense? That's the dotted line. Say you have $100. The price of X is 2, the price of Y is 1. Right? You want to graph the budget line? That's what you do. This is 50. That is 100. Right? You connect them. You automatically get a slope equal to 2. Right? You can see it's 2 now. That is 100 divided by 2. That's 100 divided by 1. For the time being, we assume the price is constant, the income is constant. But what happens if you change the income? The whole shift. Yeah, the parallel shift. More income, less income. Right? What happens if you change price of X, not Y? That's the current point. If you change price of X, what happens? The balance shifts to the right. The price is up or down. I pivoted the bottom line to the right. Is the price of X going up or down? Down. You can buy more. Down. That is up. Down. Up. Right? If you change the price down, it goes up. If you change the price down, it goes in. Make sense? For obvious reason, because this is denominator, right? Anyway, a consumer has a bottom line. They have an indifference curve. We know they want to increase, they want to go the farthest you go on the indifference curve. That's the way the indifference curve creates more. That's the way they increase their satisfaction. Suppose they went out all the way to this level of satisfaction. They chose this utility level. Make sense? Given that satisfaction level, they can satisfy the value line of these 2 points. Make sense? At point A, at point B. Start from point A. You think at point A they're optimizing? Why not? Because at point A, the MRS, the slope of the indifference curve, is it equal to the slope of that line? Yes or no? No. Is it more or less? That's the slope. It's equal. At point A, the MRS is more than relative price. What does that say? What's the signal that gives the consumer? At point A, MRS is more than relative price. Anyone? At point A, MRS is more than relative price. What does that mean? Yeah?
You buy more S because of Y.
MRS is basically how much you like X compared to Y, relative to Y. This is how much it costs you to buy 1 unit of X compared to Y. You like X more than how much it costs you to buy it. What should you do? You're probably happier to buy more. That's the signal you're getting there. So that's not an equilibrium, because conceptually you'll be happier buying more X. At point A, the signal you're getting is buy more X. Because the benefit you get from it is more than the cost. Right? You go to point B is the other way around. At point B, that is lower. So at point B, you have too much X, the benefit you get from it is lower than how much it costs you to buy it. All relative to Y. Make sense? So you cannot be optimizing there. If you want to optimize, you should move up all the way to and let's see. At point C, the MRS is equal to the price. The benefit you get from the last unit consumed and the cost of it are the same. No incentive to. Right? Make sense? So graphically optimization basically means two things. One, satisfy and its condition. Make sure the benefit you get and the costs are the same. And make sure bottom line graphically without doing much math, you know optimization means these two have to be satisfied. Right? But optimization is a mathematical concept. Right? You know from math, optimization is the Lagrangian setup. We'll see if that gives us the same answer or not. I use the graph, right? Well, mathematically, if you want to optimize, you should set up Lagrangian and solve. So mathematically, this is what you're doing. You have a utility function subject to x and y. You try to maximize it, but you have a limit. That is limited funds. Right? Now you need to choose x and y, but you're not free to choose it. You're hit with a constraint. How do you optimize now? That's problem set number 0. You should be able to set up Lagrangian. That's the Lagrangian. That's the utility you want to maximize. That's the Lagrangian parameter. Did they call it lambda there? Normally lambda. I've seen it elsewhere called differently, but normally lambda. That is the constraint. If you think about it, if you spend all your money, how much is this? 0. If the constraint is binding, this is 0. So technically maximizing of this, maximization of this one will be equal to maximization of this one. Because this is 0. So the only thing Lagrangian does is ensures the constraint is binding. This ensures you spend your money. Not more, not less. It incorporates the constraint into maximization. Make sense? But to maximize now you have to choose 3 variables, not 2. X, Y, invented Lagrangian. Right? You have to take 3 derivatives. That's 1. That gives you this one. Make sense? That's the first derivative of utility with regard to x. We call the first derivative marginal utility. So we call this one marginal utility of x. Right? For an obvious reason. This is how much you get in satisfaction from the last unit of x consumed. Everything equal. Marginal utility of x is how much you get from the last unit of as consumed, assuming y is constant. Right? So this gives you mux equal to this. Do the same thing for y. By by the same token that gives you MUY equal to PY lambda. Make sense? I can easily eliminate lambda. I made up that parameter, I really don't need it now, right? I can get rid of it. How can I get rid of it? See, the lambda is created in incorporated constraint. I don't really need to calculate it. How can I get rid of it? I can take this two and divide them. Make sense? Start eliminating lambda and end up with first two conditions together produce one condition if lambda is eliminated too. Right? The third derivative regarding the Lagrangian just produces the constraint. Right? This is called, give it a name now. That's called MRS. MRS was nothing but the ratio of two marginal utilities. So to get the MRS for Cobb-Douglas CS, I took two partial derivatives, divided them, solved it, and ended up with those formulas. For those two formulas, you have the MRS. For everything else, you have to select derivatives. Make sense? The MRS is the ratio of two partial derivatives, x and y divided. Make sense? So if MRS is 5, what does it mean? Knowing MRS, the ratio of two partial derivatives. If MRS is 5, what does it mean? It means the last unit of x you consume provides 5 times more satisfaction than the last unit of y consumed. If this ratio is 5, the last unit of x you consume provide 5 times more satisfaction than the last unit of y consumed. Make sense? Anyway, the Lagrangian sum at least tells what MRS is, right? But the outcome is the same. Use those two conditions. Fantasy, otherwise. Right? Numerical example. This is the individual. That's the individual. That's the bottom line for him. That's the bottom line for him. Find optimal allocation of funds for this individual. Right? If the question doesn't ask you, you don't have to set up a Lagrangian because you know the outcome of all those three equations. Just use those two equations. Fantasy, puzzle. So if that was the question, I would have said, I know MRS should be equal to right price. That's Cobb-Douglas. What's the MRS for it? Don't want to memorize the shortcuts. You have to calculate UX and UY, divide them, solve it. That takes time. What was the shortcut? Alpha divided by beta, yx. What was alpha? That's the power of x. Beta power of y. Yx. If you don't believe it, take derivatives. Divide them, you'll get that one. Right? That should be equal to how much? 2 divided by 1. That's the price. Right? And solve for y. That's equation number 1 solved. Equation number 2 was just about to find. Put this one there. And solve for x. How much is x? 25? Looks like 25. 25, right? That's that would be, go back there. Right? 50. I can calculate the happiness this individual gets. He gets 10, 25 to the power of 5, 50 to the power of 5. How much satisfaction he gets from consuming the optimal bundle? That is the maximum satisfaction he can never get. Mathematically impossible to do any better. What's the level of satisfaction he gets? Be honest? What's the level of satisfaction he gets? Round it.
353.
Okay. That is the satisfaction he gets. And if you graph it, it looks like this. That was the bottom line. He consumed there. That was the indifference curve that optimized his satisfaction. The level of satisfaction was about 3.5. Make sense? Okay, that is one example. Let me give you another one. So let's call this guy person A. There's a second person. Is characterized by this utility. That's the second person. That's the second person. Right? You're having the same money on a box, facing the same prices. What will the second individual do? So, one to solve for, there's the second guy. That's the utility for it, right? He's facing the same prices, having the same money. What would be the optimal bundle for this individual? Oh, all do the same thing. It's just the only thing difference is MRS, but it will change the whole numbers, right? For this individual, the MRS will be how much? That's CS. What is the shortcut for it? Yx, 1 minus alpha. Alpha is the power of x and y. That's 1.5. So remember those shortcuts. Otherwise, you have to take derivatives. And the CS has ugly derivatives sometimes, right? It takes time to solve it. So remember the shortcuts, save you time. That is the MRS for this. That should be equal to 2. So y will be equal to 4x. Right? Thus that, he has the same money, facing the same prices. The bottom line looks the same. Take this one, put it there. And solve for x. What would be x for this individual? It should be 100 divided by 6. How much is that? 100 divided by 6. Yes.
16.67.
16.67. Now y would be how much? Take this one and plug it there. That's 4 times. 66.7? Okay, there you go. 66 pounds?
0.68.
60. And we can calculate the satisfaction he gets, which should be this one. How much satisfaction this individual gets? happier? Who's happier here? The second one? The numbers aren't comparable at all. This is what we call ordinal utility function. It's not comparable across individuals. They're not like kilograms, miles, not like that, right? They're just numbers trying to order the same individual level of satisfaction. You cannot compare it across individuals. You cannot say this is happier than that. It's impossible, right? Happiness cannot be compared. These are not real numbers. This is just an attempt to order individual satisfaction through numbers. Even for the same individual, if you get a level of 500 than 1,000, you cannot say 1,000 twice happier. You just say more happier. More is better than less, but does not give you perfect numbers like kilograms and so on. So don't try to compare satisfaction across individuals. That's not possible. You know, I recall a story of a guy who had a startup and sold it while it was in the 30s. He made like millions out of it, right? He retired. There was an article about him. After a few years, they asked him how he lived and all that stuff. He had a miserable life. You know why? He said he had nothing to do. He wakes up in the morning, he calls his friend. They all work. You have to pay them to go with him on a boat ride or whatever, right? And he's just like depressed. You cannot measure happiness by anything. It's just internal, right? So these numbers don't really mean much. It just means for the same individual, more is better than less. That's the only thing it means. Okay. Anyway, we did all the way to this one. I left the corner solution. I'll define it here. We do it later. Corner solution is defined as a case when you're optimizing, but you cannot satisfy condition number 1. Tendency does not hold, but you cannot do any better. If you ever arrive at that situation, we call it corner solution. It's not going to happen if you have class number 1 functions and budget line is straight. That's what we assume so far. If you have non-straight line budget line and or class number 2 or 3 functions, you may end up with it. So I completely ignored it when I did what I did, because we have class number 1, convex smooth to the origin, and we have straight line budget line. It never happened there. Alright? So we have to go through it. We'll go through it when we define it as such. Corner solution is defined as you're doing your best, and your best in it, the first condition doesn't hold, and this does not hold. Alright? Make sense? Okay. Let's go through some questions, then when we reach the corner solution, I explain that more. I want to see if you understand the concept of indifference curve and stuff. Question 1. Crossing indifference map violates efficiency assumption. True or false? Does crossing indifference map violates the efficiency assumption? Yes or no? If we have efficiency assumption, we have completeness, non-seriation, and sensitivity, non-seriation. Efficiency assumption is in the producer theory. Later. That is false. So what's the violation then? The violation is, if you assume non-seriation, you violate transitivity. If you assume transitivity, you're going to violate non-seriation. So one of those two. If you assume you work with goods, which you typically do, you violate transitivity. What does theoretical indifference map imply? Does it mean X is inferior? Did you even talk about inferior? Indifference curve, it tells you one thing, whether you like something, dislike it, or you are neutral towards it. You don't care either way. That's the only thing it tells you. It doesn't tell you inferior, no, that's next time. That's later. That depends on income. We haven't brought it yet. So what does a so this is false to begin with. But what does a vertical indifference map mean? This is false. It has nothing to do with inferior or normal. Something else. It has to do whether you like X, dislike it, whether you like Y, dislike it. Make sense? Look. Which one you like here, which one you don't care or dislike, if you get a vertical indifference map. What does increase in Y does to the indifference curve? Does it do anything? It doesn't. A vertical indifference curve means you don't care about Y either way. More Y doesn't do anything. Y becomes neutral, nothing. Make sense? If you want to become happier, you have to get more X that push you to R indifference curve. So a vertical indifference map means X is good, Y is neutral. If horizontal mean Y is good, X is neutral. Makes sense? Okay. What about the third one? Upward sloping indifference map means X and Y must be bad. True or false? What does this indifference map mean? If someone show you that indifference map, this question says it means both are bad products. You don't like them. True or false? The answer is one is bad, not both. One, not both. Which one is a bad one then?
Why?
Why? How do you know that?
Because the consumer wants more Y for 3X.
You can have it backward. Upward sloping means more of one is compensated by more of the other one. Well, how do you know which one is the good one? You know that. It depends on what makes you happier. If that's the indifference map, does this make you happier? Then X becomes a good one. Or does this one makes you happier? Then Y becomes a good one. You cannot say which one is a good one. The only thing you know is one is a bad one. The directional increase in the satisfaction, that is the good one. So this is false. One is good, one is bad. Which one is good? It depends on what directions your satisfaction goes. Alright? Make sense? Okay. What was the last one? Horizontal indifference map means only Y must be desired. Go false. This means you only like Y. True or false? That is true. So, simple rule of thumb. Downward sloping means you like both of them. Upward sloping means you don't like one of them. The direction of the arrow tells you which one you like. Horizontal means you like Y, you don't care about X. Vertical means you like X, you don't care about Y. Alright? Make sense? Okay. So this is meat. That meat, that vegetable. A vegetarian who hates meat. If it's given, he eats it. He's polite. He throws up. How would the indifference map look for him? A strict vegetarian who really hates meat, but get it, eats it, he gets sick of it, right? How would the indifference curve look for him? It must look like this. Meat is bad, vegetable is good. Make sense? The direction of happiness is no vegetable. That's a strict vegetarian, right? Another vegetarian, he doesn't like meat, but if it's offered, he doesn't even touch it. Doesn't use it. How would the nervous not good for him? A second individual is a vegetarian too. You give him meat, he doesn't touch it. Doesn't care about it, right? Doesn't eat it. He says no. How would the nervous care look for him? Doesn't like. Meat become neutral for him, right? Doesn't give him happiness. Doesn't give him sickness. He doesn't eat it, right? Anyway. Simple rule of thumb, if you like something, you're downward sloping towards it, you give up for it. If you don't care about it, you're flat towards it. More of it doesn't do anything. If you hate it, you're upward sloping toward it. You need compensation for it. Make sense? That will allow you to graph indifference. I'll start this one, we'll take a break. We'll do more after. Figure out this individual. He's willing to exchange 4 coffee or 3 tea. Don't ask me why, just made up, right? Is it perfect complement, perfect substitute? Obviously not class number 1, it's class number 2. Extreme cases. Is it perfect substitute or perfect complement? Perfect? Perfect substitute. Perfect complement is someone who consumes both together as a specific rate. Like buying 4 coffee and 3 teas together. That's not him. He's substituting at a constant rate. That's perfect substitute. Perfect substitute, as we had it, should look like this. The MRS should be this, and you know why that's the case. The MRS is MUX, MUY. So you know why it was alpha over beta, because marginal to the X is alpha. Marginal to the Y is beta. Right? Yeah. By the numbers given here, figure out alpha, figure out beta. Right? By the 4 and 3,